exercise of what we did last time as far as the using the regression to predict this time series. Okay, so you get a little bit of the explanation why this time series is multiplicative and not additive in some way, and then the log transform that transforms products into sums, and that makes multiplicative time series as additive ones. And then a little bit of the definition of what a seasonality is. I put that in there. And then the seasonal dummy variables, so the rough one and the centered one. Okay. Of course, there are many ways to center them. You don't have, this is just one. The important thing is that you can just take the regular dummy variables, so the seasonal dummy variables, and instead of using them, you can just take that variables minus their annual mean, and that would be the same effect. So it will be different than this, but the effect will be just the same, okay? So here kind of expanded a little bit what we did, and then I talked about the sinusoid, the trigonometric way to represent the seasonality, which also we did last time. In case you read and find some mistakes, just signal that to me and I will correct it. And then finally, the code. This time I used something less brute as last time. Last time I just, if you remember, I just took for the dummy variables like identity matrices, and I just put one identity matrix below the other one. Here, for both things, I built functions. So here is a function to build seasonal dummies. Of course, you can use it throughout the course if you need it. And here I use this symbol. This is the integer division. So if you actually this is the symbol for the rest of the integer division. So if you divide a number by, for example, 12, because we have a monthly time series, then you have the rest of this number divided by 12 integer division. Okay? And using that, of course, you can find if you're in the first and the second, the third month of the year. Okay, because of course you have to like think of you have to put, instead of numbering from 1 to 12, you have to number from 0 to 11, and then you divide whatever observation here by 12, and so you always get the month of the year using this simple method. Just a way to design that. As you will see, also from, I will write code this way many times. This is called Roxygen. I don't know if you use it in R. If you comment your functions in R using this kind of small language, commenting language, you can find the instruction, of course, on the web. When you make an R package, there is a compiler for this that automatically builds the help for that function, so you don't have to write the help function. So it's easy to read in the first place, but it's very easy to use it when you want like to build an R package, right? R package. And so, well, this is the number of observations you want. This is the seasonal periodicity. Then this is true or false if you want the dummy representation to sum to 0. So we have either regular dummies or centered dummies, which is more intelligent if you want to also get the seasonal component and not just doing forecasting. And then you can tell which column you want to drop, because you know you have to drop one of the seasonal dummies to use them in the regression. And then I built function to generate seasonal dummies. Okay. And then, of course, all the exercise we did last time gets very compressed. Actually, I did it slightly differently. I just put all the y and x variables in the same data frame. And then I just did that very compactly using R. So this is just use the first 120 observation of these data sets and regress the one variable that is called y on all the other ones. And so this is a better ordered version of what we did last time as far as this regression was concerned. Okay. And here I show you that actually the forecasts are just the same in the two, because we're just representing the same information in a different way. So if we leave the full set of dummies or the full set of sinusoids into the model, we get exactly the same prediction, even the model looks like it's different. It's just the same model, but parameterized in a different way. Okay? Of course, if you select only the significant regressors, then this will get a little bit different because, of course, if you just select some of the sinusoid or select some of the dummy variables, then you don't have the same information in both models. But if you just throw away the ones that are very close to zero, so the one that have coefficients that are very close to zero, so they are not significant, then this will be very close anyway. So this is not a real serious way to make predictions, but if it's just the first step. And we'll be using dummies and sinusoids in many, many places. So that's why it was important last time that we fixed these first ideas. Maybe before moving to other subjects, other parts of the time series world, let's just do a couple of, let's say, theoretical exercises using the information I gave you last time as far as prediction and linear prediction is concerned. Because as I told you, it's not all important that you know theory, it's important that you can use it. So let's take some simple situations, simple examples, and try to find how the best, the optimal predictor and the optimal linear predictor look like, assuming a squared loss function. Okay, if we don't have better information, usually we use the squared loss function. So we want to minimize mean square errors. Okay, so let's try with a very simple example. And then after a couple of examples, I want to introduce some more information about time series so we can go on and predicting real data. There is before data. I want to show you other material I put on the learning page. Among the things you have some Shiny web apps. So I built also a couple of. I don't know if you ever use Shiny. Shiny, it's a package in some way, in our package to make dashboards. It's very handy. It's very simple to make nice and even complex dashboards. So I don't know what you usually use for making dashboard. Probably use Python. Well, actually, they're building. Actually, they built a Shiny version of for Python. So actually, using Python or R is now transparent for as far as you use Shiny. There are some application I did. One of these, it's called Sinusoid Approx. And it's just an example of how you can use sinusoids to approximate, for example, also complex and long seasonalities. So first of all, what's this time series? Well, this is a time series of the demand or the load of electricity in Italy. It's actually the original one is a hourly time series, but here I turned this into a daily time series by just picking one of the 24 hours. You can choose whatever hour you want. So actually, it's an hourly time series, but for representation reasons, I'm just using one daily time series of 1 hour. Okay. And of course, oh, this is also nice because you can also kind of zoom in the part of the data you want to see. If you're interested in how to get this, okay, this is shiny, but there's a nice, again, library for producing plots, dynamic plots or interactive plots like this one. It's called Plotly. I don't know if you know it. So, of course, there is a package to use Plotly also inside R. And the nice thing is that if you're used to use ggplot, which is very popular in R, you don't have to learn Plotly because there's an automatic conversion from ggplot to Plotly. So probably, I don't remember, I did this many years ago, but when I did this, probably I just built a ggplot and then pass it through the ggplot to Plotly, whatever the name is, and convert it. And the nice thing is that you have this dynamic plot and you can turn on and off, some time series, zoom in. Anyway, so this is, for example, just few, I would say a couple of months of this time series. It's a daily time series. We see there's a 7-day seasonality, of course, because on Saturday and Sunday, we use much less electricity than on working days because of factories and businesses are closed. So we have a 7-day cycle of seasonality, and that can be simply fit by using either the dummies that we saw or even the sinusoid. You can do it whatever you want. But there is, of course, also a within-ear seasonality, which, okay. So these are, for example, 1, 2, 3, 4, 5 years, right? No, it's just 3 years, actually. It's 3 years, and you see there is some kind of movements that they repeat within the year, that repeat themselves kind of the same way. For example, you can notice that between 2 subsequent years, you have a drop in the demand because this is Christmas vacations. It looks like in Italy they're very important. But also, this is August. So we have 2 major drops. And of course, we cannot use, so we have 365 observations, sometimes 366 observations per year. And we want to model also this slowly changing seasonality due to how much light or how long the day is, how warm or how cold is it. So, so you kind of see the shape due to, so the maximum you reach in winter of consumption, of course, because there's not so much light. In Italy, we don't use much heaters, electric heaters, so that's probably not an important thing. But anyway, there's a peak around January, February, and then it decreases till, I would say, probably May and June, and then it starts going up again because of air conditioning. Air conditioning is probably the thing that consumes electricity the most. And then everybody suddenly goes on vacation. This is very Italian. For example, Nord Pool time series. Nord Pool is the Scandinavian market for electricity, you don't see this. Okay. And then it goes back on September, not so strong because it's air conditioning usually is off, and so on. In order to model all this typical variation you see throughout the year, you cannot use dummy variables. You would need 364 dummy variables. You cannot have 364 variables for maybe you have 2-3 years of data. That doesn't really have any sense. And even more, you have this second seasonality, this 7 days seasonality that would also kind of get into the problem if you don't model that first. But if you model with 365 or 64 dummies, then you also have a problem because the seasonal dummies are a subset of in some way of that. But anyway, so the solution for modeling this kind of seasonality is through the sinusoids. Of course, we don't need all of them because this seasonality changes rather smoothly. And indeed, I superimposed 2 lines here. Well, the yellow line is just a linear or quadratic trend, whatever. But then the orange line is just a moving average. So I'm taking like a local average and move it, right? And how long that average is, you can actually decide from here. So I'm taking 21 observations. So we can even take it only 7, so that we kind of throw away the seasonal variation due to the 7 days. And of course, the orange line becomes more rough, but you still see the main seasonal variation. Well, of course, you get also some other information. This could be Easter vacations, for example, and they keep on moving. And what's the red line? Well, the red line is a set of sine and cosine functions. How many? Well, you decide here. I just put 10 of them. It looks like that already 10 of them are kind of they're moving very similarly to the moving average that is kind of smoothing out locally the time series. So it looks like that if I use maybe 10 sinusoids, I already doing a good job in modeling the within year seasonality, okay? Of course, you don't get the peaks, the negative peaks in August, because sinusoids, as I told you, they're very good at modeling with just few sinusoids. Smooth functions, they're not so good for modeling abrupt changes. So you can use a mix of the things. For example, here we could add a dummy variable just for the August weeks of vacation. They're predictable. So. But this just to show you that sinusoids, they are doing a good job. Maybe we could go up to 20 and get a better fit closer to the orange line. And some of you may say, okay, but why don't we use then the moving average if you say that is a good example of extraction of the seasonality? Well, because moving average are not for predicting. They're just, you can just do them within the sample, but we want to have something that we can expand in the future. And while sinusoids I can expand in the future, what about the moving average? They're just smoothing the data, so they're not able to do predictions. Okay. So you can play a little bit around with this application, whatever you want. It was just a simple way to show you what you can get with sinusoids. Of course, if you put many sinusoids, you start also modeling the 7 days seasonality. But that's a problem because if you divide 365 by 7, it's not an integer number. We know that. We know that the first day of the year is not always the same weekday, okay? And so the two seasonalities are not one inside the other one. And so that's why we have to model them in a separate way. And the problem is that, of course, if I put too many sinusoids, I start approximating also this other 7 days seasonality, but we do it in a very bad way because we don't have the right frequencies to model them. And you see that actually getting the peaks very badly. So you have to pick, a right amount of seasonal cycles, so sine and cosine functions. Okay, we'll get back there again on this. Some concepts I want to get back in many lessons because they're important. Okay? So be acquainted with sinusoids. They're very useful. Last time I told you there's also other methods based on splines. Yeah, I didn't explain those. We may try to see something about splines later, but these are the main tools that usually are used in these applications. Okay, let's go to the other exercise, and then we can, what's this? And then we can go on with some time series concepts and applications. So, so last time, if you remember, we saw two types of predictors. The optimal, say, the overall optimal predictor. Let's first assume we use the quadratic loss function. Okay. So this is the usual loss function if no better loss function is provided, okay? In this case, last time we saw that the best according to the loss function, predictor function of the data, so the vector x, is the conditional expectation of y given x, while if we just look at linear function of x, of the data, so the best linear predictor, so of x given x, y given x, is the linear predictor, which I'll recall it's just the mean of y plus the covariance of y with x times the inverse of the covariance of the x vector x minus its mean. Okay, and we also know the mean square error of the linear predictor, which is just the variance of y minus the covariance, the variance of x inverse. So these are the formula we saw yesterday. Now let's try to do a, let's call it theoretical application, meaning that we're not using data. So suppose that we have x, which is a normal random variable, a standard normal random variable. Then we have like zeta, which is again a normal random variable or standard normal random variable. And suppose that x and y are orthogonal. Orthogonal here means independent. Actually here, zero correlation and independence are the same, because if x and zeta are jointly Gaussian, we know that independence and correlation are the same thing. That's only right for a Gaussian distribution. But anyway, let's suppose X independent of Y. So you can read this orthogonal symbol by meaning they're independent. Okay. And let's assume that our Y is generated by x squared plus zeta. Okay. So my first question is, what's the expectation of Y given X? Well, it's extremely simple. I would say that most of you should be able to say right away which is the expectation of Y given X. But anyway, let's substitute instead of Y the definition of Y. Okay. Okay, X is known because we are conditioning on X. Okay. So of course, X squared gets out of the expectation. And what about the rest? Well, we have the expectation of zeta given X, but we said that X and zeta are independent. So knowing X tell me nothing about zeta. So the expectation of zeta given X is just the expectation of zeta. And what's the expectation of zeta? Well, 0 by definition. So that's it, okay? So the best predictor of Y given X is just X squared, of course. Yep. Sorry, zeta. Yeah, I wrote Y. Sorry. Yeah, of course. Y cannot be independent of X. We're defining Y through red. Okay, so this is the best predictor, which we can see it from here. It's straightforward. If this is the mean zero error, this is going to be the best predictor. What about the linear one? Of course, the linear one will be not as good as this one. Well, if they're equivalent, they're both as good, but usually the linear predictor will be less precise than the optimal predictor. Oh, okay, just one more step. What's the mean square error of this predictor? Well, it's simple again to compute because we just have to compute this Y minus X square. Well, X square is the predictor, okay? So this is the mean square error of the predictor. Okay, let's write, instead of Y, its definition. And then we have the square here. This simplifies, so we just have zeta. So we have, well, zeta is mean 0, so this is just the variance of zeta, and the variance of zeta, again, by definition, is 1. Okay. Now let's move to the linear situation. Linear situation, we can only have linear functions of x, so we cannot reproduce x squared because x squared is not linear. Okay, so we are using x. We're not using x squared. If we use x squared as a feature, as a predictor, then we would have the same result. But we are just using x because we don't know what's the best model. Usually, just assume x is a good predictor for y for a linear model. So what we need is, we need the mean of y. What's the mean of y? The mean of y is just the mean of x squared plus the mean of zeta. Well, zeta is mean 0, so the mean of zeta goes away. And what's the mean of x squared? Well, x again has mean 0, so x squared is the expectation of x squared is just the variance of x. So it's going to be 1, okay? So the mean of y is 1. Then we need the mean of x. Well, the mean of x we already have by definition, but it's 0. It's 0 because we defined it to be a normal of mean 0. Okay. Then we need the covariance of y and x. That is, in theory, I should write this like this, right? Okay. Actually, in this case, I could just write the expectation of y times x. Does anybody know why this, or if you don't know why, you can try to prove it. I'll just give you a very short rule, then you can try to prove it. If any of the two variables is mean 0 and x is mean 0, then you can just drop also the other mean and you get the same computation. Okay? It's very easy to prove because you would have expectation of y times 0. I mean, if this is already mean 0, and you decompose this into the product, the expectation of x to the x. This is the constant, so constant times the mean of x. If it's 0, it's going to be 0. That's why. In this case, this holds. Just in this case, just if one of the two variables has mean 0. Okay. So let's now substitute. Instead of y, we write the definition of y, which is x squared plus zeta, and this multiplies x. Okay. So at the end of the day, we have the expectation of x cubed plus the expectation of zeta times x. Well, this is clearly 0 because they're independent and they're both mean 0. So if the two variables are independent, the expectation of the product is just the product of the expectations, right? If they're independent. And we have the expectation of x, which is 0, and the expectation of zeta, which is 0. So 0 times 0 is just 0. What about this? You should know this as well. So what's the expectation of the third moment of a standard normal distribution? No, yeah, skewness, right. Which is? Well, all symmetric random variable have the same skewness, which is 0. If they're symmetric, it's 0. Okay. In theory, we should also compute the variance of x, which we already know it's 1. So now we can put all the pieces together to build the predictor. So the linear predictor of y given x, it's the mean of y, which is 1. We just computed here. So this is the mean of y plus the covariance between y and x, we just computed to be 0. Well, times the inverse, this is just a scalar, so it would be divided by the variance of x. The variance of x is 1. And here we would have x minus, well, the mean, which is 0. Okay. So the best predictor in this case is just 1. It's just the mean. From the intuition point of view, it's pretty clear. You cannot predict x squared using x, because if x is positive, it's growing. If x is negative, it will be decreasing. And of course, on the average, it will be 0. So that's exactly. So our best guess, just using linear functions of the x, is just y is equal to the mean. This is just because it's the y and x are uncorrelated. Of course, if your target variable y is not correlated with the features you want to use to predict y, then the linear predictor will just fail. It will just be the mean of y, okay? And what's the mean square error? Let's compute also the mean square error. Well, the mean square error, of course, why? It's very intuitive. We could use the formula, but it's very intuitive. If my prediction is that just the mean of y, then the mean square error will be just the variance of y, okay? But anyway, so what's the variance of y? The variance of y, let's try to compute the variance of y. So it would be the square, the expectation of the square of y minus 1, okay? So this is the variance of y. Again, we substitute instead of y, we put the definition of y. Okay, then we have well, we could see this. Well, we could do all the computation, of course, and if you want, we can do that way, or we can like see that this would be the variance of x squared plus the variance of zeta. And then there would be the double product between these two, but that would be 0 because x and zeta are independent. Oh, sorry. Or you can just take the square of all the terms and take the expectations. So I just took these two together plus zeta, okay. This is just x squared minus its mean. So I took the square of that thing. Then I took the square of zeta. No? And then we would have, of course, the double product of this times this. But x and zeta are by the definition independent, and zeta has mean 0. So that is 0. If you want, I can write it. So we would have 2 times x squared minus 1 squared times not square, times zeta. Okay. But these two variables are independent, so the covariance is 0. And this is a covariance because zeta has mean 0 and x squared minus 1 has mean 0. Okay. So this is 0. So we're just left with these two terms. And this is just 1 because it's the variance of zeta. We just have to compute this one. And now we can do the square of this one, which is x at the 4th power plus 1 minus 2x squared. So the first term is, what is the 4th moment of the standard normal distribution? The 4th moment. Kurtosis. What's the kurtosis of the standard normal? 3, right? So we have 3 here. Then we have just plus 1. And then we have minus, and this is the variance, so 2 times the variance of x, which is 1. And so we're just left with 3. So at the end of the day, we have 3 plus 1, so this is going to be 4. The variance of y is going to be 4, and of course, it will also be the mean square error, because the mean square error of the linear predictor is just the variance of y minus the covariance times the variance at -1 plus the covariance, but the covariance is 0. Of course, we're not doing better than the mean because we're predicting with the mean. So if we are predicting with the mean, the mean square error will be just the variance of y. So this is the mean square error. And you see it's much larger, of course, than the other one. The other one was 1, and this is 4. Okay. So we are doing a really bad job by predicting a squared function by a linear function, which is intuitive. So in some cases, linear approximations are good. In some cases, they're very bad. And try to solve this other problem. Again, take x and y and zeta independent standard normal random variables, and this time you can define y as being the product of x times theta. And we want to predict y based on x. Try to compute the conditional expectation. Again, we can do exactly what we did before. So instead of y, we write the definition of y. X times theta given x. Okay. Well, x and zeta are independent, so actually we can write this. Well, yeah, we can write it as actually, I don't even need to do that because this is x belongs to the conditioning variable. So actually x can get out of the expectation. So we just have the expectation of zeta given x times x. Okay. This is one of the property of the conditional distribution. Of course, you can take out of the expectation the quantities that you know because you're conditioning on them. Okay. So x can get out of the expectation. So we just get expectation of zeta given x, but they're independent. So the expectation of zeta given x is just the expectation of zeta. And so there is no way you can predict this y. It's the mean, of course. And in this case, even the conditional expectation, if you just know the x and you have a model that works like this, the best prediction you can do is just do it. And of course, you can check also the linear predictor would be the same because you will see that there is 0 covariance between y and x. But of course, if they're independent, they're also, I mean, they're not independent, but the expectation is going to be. I can give you maybe a few of these exercises on the e-learning also with solutions, so you can try to get acquainted with this kind of operations. Again, these things will be done in time series analysis, so it's good if you are they're just games, they're just simple games. You have just to remember sometimes properties of, in this case, the normal distribution, maybe higher order moments, but you can find on Wikipedia really easily, and so on. So instead, let's move to more time series analysis things. So let's start with some definitions. Okay, now for a while we'll be mostly statisticians. So we'll be looking at, so what's the difference between a statistical model and a machine learning model? It's just the approach. At the end of the day, you come up with algorithms to fit a model to a data. But the model in statistics usually are thought as data generating models. So you think of a reasonable or an approximation of a reasonable model that produces the data you will then see. Okay, so the mechanism the stochastic mechanism that produces the data, you design, and then you try to build the best estimate of what is missing in this model, because in statistical models some things are missing. So you have to estimate the missing parameters of the model, and if you want to do forecast, then produce the best forecast you can with that model. A machine learning model doesn't pretend to be able to generate the original data, but it's just a very general algorithm to try to find nonlinear functions of the x to predict some y, but you're not pretending you know the stochastic way in which the y's were generated. Okay, that's in some way in statistics you would call that an unparametric model. So a model where you don't fix the distribution of the data, but you try to understand the distribution of the data from the data themselves. But anyway, so let's start with this vision. So we want to try to build models that probably are good approximations to many of the processes that are generating time series. Okay, so we will be seeing a time series as a sequence. Well, is, for a moment we will just consider that is of random variables indexed by time. So a time series is just a collection of random variables, with t being the time, which in our case it will be discrete. Okay. We will have to do just with discrete time series. Okay. I mean, in computers you can anyway analyze only discrete numbers, but of course time series you can also address continuous time random variables, and they're called continuous time stochastic process. But in our case, t will be just an integer number. I just put the positive number. You could also take also negative. That doesn't really matter. Okay. So if we want to just be more precise, we can say, okay, t belongs to zeta, so the set of integer numbers. But they are random variables, so they take with themselves all the theory of random variables. Okay? The point, which is very strange in some way, is usually in statistics, you build you suppose there is a random variable, and then you have a sample of this random variable. It means that you've observed realizations of these random variables for, I don't know, 100, 1,000 observations or more than that. Okay, so suppose you're interested in the, I don't know, how tall an adult male Italian is. Okay, so there is the random variable, which would be if I sample randomly from an Italian, I will get the same distribution of the length of the people as the one in the population. So I will have, I don't know, 100 persons, and then I will take, for example, the mean, the variance, to estimate the same quantities inside the population. But in time series, we have a problem. The problem is that actually we only have one sample of the data, because of course we in time series we will have, I don't know, from x1 to xn. But at the moment, I didn't tell anything about this random variables. They could be, any of these random variables could be completely different than the other one. It's just a sequence of random variables. They don't have to share some properties in time. So if I just define a time series to be a sequence of random variables, and then I pick one sample, a time series sample of this observation, any single number x1, x2, xn will be just a single sample of the time series variates, which is representing, okay? So in time series, we have, you may also see it this way. Sometimes in probability, you say, what is a random variable? Well, a random variable is just a function of some event omega, okay? So for example, you throw a dice, and the event is, I see above 3 little balls. Well, and then you associate that 3 little balls with the number 3, okay? So the event is I throw dice and I see that figure on the top, and then I, of course, take that and set it equal to 3. So this is like throwing the dice, okay? And in time series, you may think that as I throw one dice, and according to the number that come, or the phase that I see, I pick the whole set of numbers going from observation number 1 to observation number n, okay? Or maybe you can visualize it. You take like a necklace, and you throw the necklace, and you see the, I don't know, if you throw the necklace on a table, for example, you could measure how far away each pearl on the necklace is from the x-axis, and you will get a time series measure of this, where the single pearls in the necklace fell, okay? But you throw that just once. You're not throwing many times each, the first pearl, the second pearl, third pearl, okay? You're just throwing the whole necklace at once. So you just have one observation, one random event is influencing the whole time series. You can see it this way, okay? So that's a big problem, because in order to do inference, so to understand some regularity of the time series, we cannot base inference on just one single sample. So it's crucial that in some way we assume some continuity between the past and the future in some way. Because if the past and the future are completely different, then knowing the past is telling me nothing about the future. And this is exactly, if I like throw the whole necklace and I see only half of the necklace, I cannot say much about the future of the necklace if I don't assume some kind of continuity. Well, a necklace in some way has already some continuity because there's only one, let's say, I don't know, how would you call it, file, what, or ribbon, whatever there is. Okay, well, right, there is just one thread connecting all the pearls. Thank you. Okay. That's in some way even better. The situation, the example of the necklace is better than reality. Okay. So we have to assume some kind of, as I told you, similarities between the axes here. Okay. And so the first definition we are going to give for working with time series in a statistical way, but also with machine learning, you need that. Is this kind of continuity between past and future? Well, one assumption, which is very important, is the assumption of stationarity, okay? And of course, stationarity, there's more than one definition of stationarity. There are like stronger and weaker definition. I'll give you both of them. So a time series is so this is the weaker definition of stationarity. If the expectation does not depend on time, so it's got the same mean, okay? Whatever t I pick, the mean is the same. And the covariance between xt and xt minus h is only a function of h. Usually it's called gamma of h. And of course, the variance is just a special case, because if you take h is an integer number, okay? H integer. Okay. If you take h equal to 0, then this is the variance, okay? So the variance, the constancy of the variance belongs to the constancy of the covariance function. This is called the covariance function. Or you can write it also either so, or if you like this better, okay? It's just the same thing. Pick whatever you want. Well, this is just relative, so this is more time series because it looks like I'm looking if there is dependence between the time series and its past. But this is just the same. So pick whatever definition you like the best. And actually, since the covariance operator is a symmetrics in the argument, well, also the function gamma is symmetrics with respect to h, and so actually this is true. We can just look at the absolute difference between t and s. This is simple because you can change the order. So this is the definition of stationarity. It's a very strong definition, of course. It's telling us that the mean of the time series is not changing in time. The variance is not changing in time because, again, if I put h equal to 0 or t equal to s, I get the variance. And I'm telling you the time series or the random variables that are generating the time series, they do have the same variance over the time. And also the memory, let's say the linear memory, because covariance or correlation are just the linear memory of the time series with its own past. And so the linear memory of xt of its own past, xt minus h, is constant, does not depend on time. Okay? And the problem is that, well, this is just a weak definition of stationarity. I can give you a stronger one, but even the weak definition of stationarity sounds to be too strong for real data, right? I mean, if we go back to our air passengers time series, so let's look at that. So does this look like a time series which is generated by a stationary stochastic process? Not much. Can we assume that the mean is constant? Not really. It's growing, so it's not constant. Can we assume that the variance is constant? No, it's getting more and more variable as far as the time passes. Of course, the covariance, it's harder to check, but that would be hard. So, of course, stationary processes are just one part of the process that we're interested in. But they're certainly important because, of course, on a stationary process, I can think of estimating, for example, the mean and the variance and also the covariance using the sample mean, the sample covariance, or the sample variance, because under some conditions, like the law of large numbers may hold also for time series, okay? So sample means and sample variances, covariances, they also converge to their population counterparts. So we have to find a way to make this look like the one that we're able to do some inference on, so the stationary time series. There is one more motivation why this is not stationary. Suppose we do what we did last time. So we take the log and we take the difference. So we take air passengers. We first take the log and then we take the difference. You probably know the pipes here. Oops, I didn't plot it. Okay. So, is this time series stationary? Well, the mean seems to be pretty constant. Okay? The variance seems to be pretty much constant. I don't see higher variability here than here. Okay. But is this time series stationary? Looks like it could be stationary. There is just, but just by reasoning, what's this time series? Well, this is the log increment of, for example, the number of passengers of July with respect to June, then the increment of August with respect to July, and September with respect to August, and so on. Well, there is seasonal variation here. Of course, we see it. We see the negative peaks are always on the same month. The positive peaks are on the same month. Well, this is violating also the constancy of mean. Because if I can tell you that if I look at July, the mean is different, all the Julys are, I don't know, higher than all the Novembers, then it means that November and July, they don't have the same mean. And so I'm violating one of the assumptions which are equal mean for all the random variables, okay? So seasonality is also a form of non-stationarity, okay? That one has to deal with. So the important things of a time series are those that are non-stationary. But anyway, we have to go through those definitions and then build on them, okay? But for example, suppose that instead of taking a difference, if you remember, I defined last time or 2 lessons ago, so the difference, which usually you use the symbol for, is this operator here, okay? One thing, notice that we're working on log, the log of data. So the difference between becomes a relative thing. So when I read 0.10, it means 10%, circa 10%. When I read minus 0.2, it's minus 20%. Okay? Anyway, because we just took the log. Of course, I could also take the so-called seasonal difference. So what's the seasonal difference? Well, it's a difference where instead of taking the 2 adjacent observations, I take the difference between t and yt minus s, where, for example, in our case, we have monthly data, so our s is equal to 12. Okay. Well, that, if you reason on that, that could also kind of make that time series stationary, because if I compare, instead of comparing this month with the previous one, and the numbers usually are very different from month to month. But if I take the same month of last year, probably the difference would be kind of close to the trend, because probably all months tend to grow at the same pace or a similar pace. And so we could take, instead of the difference, we could take the seasonal difference. Okay. Well, the mean could be constant. Maybe it could be constant. Maybe it's slightly decreasing, but okay, let's assume it's kind of constant. The variance probably, okay, it's kind of homogeneous. And now we don't have seasonality anymore. So this could be a stationary time series. Could be. We can check. Of course, it's very persistent. What do I mean by persistency? Let's assume, let's take a mean. For example, I can add a mean to the plot. Oops, I switched the two things, sorry. First the log and then the div. That's bad. Okay. Strange. That doesn't look like the mean.
Because the 12 is in the wrong parentheses.
What?
The 12 is in the log parentheses,
Ah,
not in the div.
okay, that's why. No, it's in the div.
So in the,
Ah, okay, that's a warning. Ah, okay, thank you. So you're right. Okay, now that's right. So this is the mean of this, the sample mean of also the time series. Again, it's about 0.11 or so. It means that, okay, now the difference are with respect to the previous year. So it means that if I read 0.10, it's 10% increase with respect to the previous year. Okay, not more to the previous months, but the previous year. So that's why it's larger. And so the mean it's about 11–12% growth. So it's a mean growth of 12%. Okay, can't read it this way. But anyway, I didn't want to show you this. I wanted to show you that there is some so-called persistence. So if you compare this with random data, they would like oscillate randomly above and below 0. Here you see that if I'm above the mean, I tend to stay a long time above the mean. This is not random, okay? And again here, so there are long times in which I stay above or below the mean. I mean, by this means that the time series is kind of persistent, okay? And we will see this has to do with the correlation of observation with their own past, okay? But anyway, this probably is close to being a stationary time series. So stationarity here could be a good approximation to reality. And if we are able to predict this time series well, then we are also able to predict the original time series because all this transformation that we took, they're all invertible. So I can take I can integrate. What does it mean? I can integrate. Well, this is, if I predict this time series, I'm predicting the early increments. So if I have a number predicted here, it means that that number I have to sum to the time series 12 months before that time. So if I take the original time series 12 months before the time is predicting and add my prediction, then I'm predicting the original time series. And then I also have to take the exponential, okay? So all these transformation that we took are invertible. So actually predicting this time series means that I can also predict the other ones, but the other ones were not stationary. This is stationary. So I have many models I can use for this time series. And then I back transform the time series so that I get to the original matrix, and I back transform also the prediction, okay? Again, remember, I mentioned to you, remember that sometimes when you take a nonlinear transformation, you're not more predict. If I predict with condition expectation here, but then I take the exponential, I know more predicting with the condition expectation on the original time series. But anyway, there are all things we will put together. Is that clear? Any questions up to now? Are you following? Good. So we have to keep in our toolbox difference, seasonal difference, logarithms. These are all useful things we will have. So we are kind of filling up our toolbox for doing predictions. Okay. Going back, for example, sometimes I want to throw you some information about machine learning, even though machine learning we keep for the last part of the course. But again, if we use something based on trees, on regression trees, the original R-line time series, we said there's no way you're able to predict that using trees, because the trees will be able to reproduce only the range of data they have observed in the training sample, right? So this transformation could be also good for if you want to predict using method based on trees like random forest and so, because this stays pretty much in a fixed range. And in that case, I can use a method based on random tree or regression trees, okay? But the original time series, as I told you, was not predictable using the tree. So sometimes the same transformation we use in linear time series analysis are also useful for machine learning, okay? So keep that in mind. Good. Then I give you a stronger definition of stationarity, which we are not going to use that much, but it's good that you know it. So in some way, what is a weak stationarity? It's just constancy of the first two moments of this time series of this. So if I generalize this definition to the whole distribution of the data, then I have the strong version of stationarity. I'll call it Y, okay. I call it X instead of Y. Let's use the same letters. Sorry about that. Let's see. So means that you can take any subsequent of this time series. They don't. It doesn't have to be a sequence in order the sequence. I mean, you can take any how do you say of time indexes and just uh, shift that time indexes by a fixed time h, and you have the same distribution of the data than you from stationary. Okay. Of course, that is true also for the marginal. So if I take the distribution of the first y, that it must be equal to the distribution of the second y, and it must be equal to the distribution of the third y, and so on. But this is of course, every joint distribution of any capable of time series observation. So the first one has just to do with the first two moments. This has to do with the whole distribution of the data. But this is, of course, not very handy to use. So usually we work with weak stationarity. Good. So this is in some way the first way we define some continuity between past and the future. What about? So we saw that in real data, if I take differences, I get rid of some forms of non-stationarity, okay? We just saw it. I didn't define anything, but I went there on the data, we took the log, we took the difference and so on. So there must be a class of process that in some way can be transformed into stationary process, but that originally are non-stationary. And this class, for example, is the class of integrated. We will be using the word process and time series as if they were exchangeable. Okay. So what's an integrated process? So we can define it this way. Integrated of order D is usually symbolized by these letters. If yt is non-stationary, if I take d minus 1 differences, we will see now what means taking d minus 1 differences. I should have defined that before, but anyway, is non-stationary. But if I take d differences, so in practice, a process is called ID if it's non-stationary and the minimum number of different types to take to make it stationary, it's d. D minus 1 is not enough. So what does it mean that I take 2 differences, 3 differences? Well, it means what it means in English. I take the first difference we already defined. Okay, so I take yt minus yt minus 1, and I get a new time series. Then I apply the difference to this new time series, and that's the second difference. And I get a new time series. And if I apply 3 times the difference, I have to apply the first difference to the result of the 2 differences. Okay. So basically, it's the sequential application of the differences. So I introduce you also a new symbol, which is called the backward shift or the lag it's different in different disciplines. I mean, usually statisticians use B. And if you apply B to the time series YT, you get YT minus 1. Okay? It's just an operator. Of course, it acts on the whole time series. Okay, so it would be more correct to like write the whole sequence of times. So, but anyway, usually we don't use all. We just use this single logic. Okay. For example, in econometrics, they use lag as log, L as log. Okay. Engineers, they use D as delay. Okay, it's the same thing, but every discipline has its own symbology. I usually use B or L because I'm a statistician, but I work a lot with economists, so okay, whatever. I think in the book I use B. For example, the difference, the simple difference, you can write as an operator, which is an identity operator minus the backward operator, right? Indeed, if I apply this to YT, so the identity operator gives you YT, and the backward lag or backward shift operator gives you T minus 1. Okay. This kind of operators are everywhere in the time series literature because they make things easier. In many situations, they make things simple. And for example, the nice thing about these operators, they're operators, so they are not variables, but they enjoy the same algebra as if they were real or complex variables. So even though I have just met this operator and this operator as well, and the identity operator and so on, you already know how they work because they share the same algebra as the real variables, for example. And I'm going to illustrate you in a couple of times why this happens. For example, suppose we want to take two differences. So this means that I want to take the difference of YT, okay? So let's apply the first difference, and I get YT minus 1, right? And then I have this difference operator, which I have to apply to YT and to YT minus 1, okay? So I have YT minus 1 minus YT minus 1 plus YT minus 2. I'm applying this to this and then to this, okay? So this is the result for this part, and this is the result for this part. Okay. So at the end of the day, taking two differences amount in taking YT minus 2 times YT minus 1 plus YT minus 2. So beware, when you apply a second difference, you're not taking YT minus 2. That's the seasonal difference. If you take 2 times the simple difference, you're taking YT minus 2 times YT minus 1, and then you add YT minus 2. This kind of recalls of the square, right? Indeed, if instead of applying the operators sequentially as we did, we tried to go with the algebra we already know applied to sigma square. So this is the operator. let's just apply the rule of the square to this thing. And we treat, of course, the identity if it was a 1, okay? So I get just y, the identity, then I have minus 2 times the identity times b, and then have plus b squared, right? And of course, if you apply this to y, you get exactly the same results that we obtained before. Okay. So you start seeing that actually these operators, they behave, if they were variables, but remember that they are not variables. For example, it doesn't have any meaning if you put yt times this thing here, because they are operators, they work in that direction, in this direction, okay? But it's good because the algebra we already know. It's the same algebra we're been using from the school, okay? And so this is the definition of an integrated process. And in some way, we have seen a special case of integrated process. We've seen a seasonally integrated process. We will go on defining that. But I'll just end this lesson with one final example. Do you know this process? You know, have you ever seen this process? It's a random walk, right? It's called random walk. It's in some way, it's a process where the best prediction you can do of the future is this last observation you have. Okay. For example, it's pretty much used in finance, for example, because in finance, in some way, you think the price of an asset in every moment t should contain all the information that is available at that time. And so if all the information is included in the price, there is no way to predict the price. So my best prediction is just the last price is the best prediction for the next price. Okay. Okay. This is a, for example, this is called random walk. Can you see that this is an I1 process? So what's the difference of this process? What if I take the difference of yt? What I get? What do I get? Well, if you take the difference, you just need to move this on the other side of the equal sign. So this is the difference. And the difference is equal to something that is fixed. I didn't tell you. Okay, I forgot to tell you one part. Okay, this is called, well, this is IED, but anyway, if I don't assume IED, but only this, oh, okay, sorry, this was already contained here, sorry, because I told you that it's IED. I gave you actually too much information. Let's take some information. So a random process with this property is called white noise, okay? Rumore bianco, so this is white noise. It's a process whose mean is 0, whose variance is constant, and doesn't have any covariance or correlation with its own past. Okay. And if you take the first difference of a random walk, you get the white noise. And the white noise, of course, is stationary. It's all here. I mean, nothing depends on t here. Okay? So a very simple example of a I1 process is this random walk. So it's not, we try to, as an exercise, now we stop here, but as an exercise, for example, assume that the first observation, so y0 is 0, and prove that the variance of the random walk is non-constant in time. You will see that the mean is actually constant in time, even though the mean doesn't have a very strong meaning here, but you will prove that yt, the variance of yt increases with the t. So the variance is, and so you have proved that it's non-stationary. To see that it's stationary, the first difference is stationary is immediate because you just get the white noise, and white noise by definition is weakly stationary, okay? So just try to prove that it's the yt is non-stationary. This is what it's missing from this picture. Okay? Good, we stop here because we have to run. And if you have questions here.